Let us see how we can use the boost converter as a power interface for MPPT. Consider this photovoltaic module, and this photovoltaic module is now interfaced to the load or not by a boost converter. Boost converter is having an inductance at its input, a switch, a power semiconductor switch like this. Now this could be a BJT as shown here, or it could be an IGBT, or it could be a MOSFET. Any of the switches, any of the power semiconductor switches can be used here in switched mode, on off mode. So this point, from this junction we need to use a diode connected to a capacitor, output capacitor. So this portion forms a boost converter circuit. Now to the terminals at the output of the boost converter, you connect the load, the application load, like this. So let us name the parts. So that is R0. Here is the terminal voltage Vt, the inductor L. Let us say the current flowing through the terminals, the PV panel is IT. The same IT is flowing through the inductor. So IL is same as IT. We call the switch as Q, diode D, capacitor C, and the output voltage V0. Now let me draw a timeline T, and I will mark by these ticks as shown the distance between these first two tick, that is called TS, the time period, the switching time period. So it is with respect to the power semiconductor switch Q. This is the switching frequency of Q. 1 by the switching frequency is TS period. Likewise, this is also another TS period. Now the TS period itself is subdivided into two parts. The switch is on and the switch is off. So let us mark with another tick here, and this period we will say is DTS. D is a value less than 1, 0 to 1. So DTS is the time when the switch is on, and obviously 1 minus D, TS, will be the time when the switch is off. So we'll say this is the on time of Q, Q on, and this is the off time of Q. Now consider the on time. When Q is on, what happens? When Q is on, the current flows through in this path during that time. So current flows like that. Not only that, this current flows like this. The capacitor is also continuously discharging to the load. So this is also happening. The diode is off because this is at V0 potential. This Q is on, so this is at ground potential of the circuit. So the diode is reverse bias, diode is off. So you have like two separate circuits. One, the PV charging up the inductor like this. The C, the capacitor, discharging to the load in this fashion. So during the time when Q is on, we can observe the voltage across the inductor and the current through the inductor. These are critical electrical parameters that you need to know about any converter. So let us say you have the voltage across the inductor measured in this fashion, measured with the ground common probe of the oscilloscope or the multimeter from here, and the positive probe of the oscilloscope here. So this would be VL and that will be IL. So VL, if you take when during the time when this is on, this is at 0, this is at VT, so you will have VT voltage coming across during the on time, and during the same time the current flowing through the inductor is same as IT. The current, because this is VT is constant, the current will be linearly going up, because VL is equal to L dIL by dt. IL will integrate, and you will see the current waveform going up like that during that time. During the time when Q is off, but the inductor current has to continue to flow, so it will change polarity here and it will drive this diode on and charge up the capacitance, and also the current will flow through the load and supplies the load. So you will see that the inductor, the stored magnetic charge in the inductor will discharge both through the capacitor and the load, and charges up the capacitance. The voltage across the inductor now will be Vt on this side, and on this side diode is connected to the output, so it will be V0, so Vt minus V0. As V0 is greater than Vt, you will see that the voltage across the inductor would have gone negative, and this is expected because we need the positive portion to balance out the negative portion, so that the average voltage across the inductor is 0. And the current through the inductor will decay, because this is discharging now into the capacitance and discharging into the load. Capacitor is charging up, so it will flow in this manner and then repeats every switching cycle. The waveforms repeat every switching cycle in the steady state, and the average inductor current, the current that is flowing through here, will be the terminal current IT. Let us make some space and let us try to find what is the input-output voltage relationship. The input-output voltage relationship means relationship between Vt and V0. We will use the property that the average voltage across the inductor should be 0, cycle by cycle, in the steady state. So if you see the voltage across the inductor, this is the waveform. It is Vt positive during dTs, it is Vt minus V0 negative during 1 minus dTs. These two areas should balance out. So therefore, if we write here Vt dTs, so the area here is Vt into dTs, the area here is Vt minus V0, so Vt minus V0 into 1 minus dTs. The time intercept is 1 minus dTs. So these two areas should add up to 0. So if you simplify that, you will get V0 is equal to Vt into 1 by 1 minus d. Now that is the voltage relationship between the output and the input. Output V0 is given by Vt, the terminal voltage across the panel, into 1 by 1 minus d. Next, what is the input-output relationship? The current relationship. See, for the voltage relationship, we used the volt-second balance, across the inductor. Likewise, For the current, we use the amp second balance of the current through the capacitor. You see that just like you have the average voltage across the inductor to be 0 every switching cycle, the average current through the capacitor has to be 0, meaning that there should not be charge buildup in the capacitor in the steady state, charge buildup or charge loss. So therefore, in the steady state, let us say the current through the capacitance, let us look at that. So during the time when Q is on, during DTS, the diode was off, current was discharging. If I say positive direction of current is flowing into the capacitor to charge it up, current discharging as a negative current, so that is value equivalent to I naught. So minus I naught into DTS is the capacitor discharging, plus during the time when Q is off, the whole inductor current is flowing in this path through the diode, and a portion of it charges up the capacitance and the portion of it flows through the output resistance I naught as I naught. So IT minus I naught is what is flowing through the capacitance to charge it up. So it's IT minus I naught into 1 minus DTS. So the charge up and the discharge should balance out cycle by cycle, so that is equal to 0. So this on simplification leads to I naught is equal to IT into 1 minus D. This is the second important relationship. One is the input output voltage relationship, the other is the input output current relationship. So that is 1 and this is 2. So if you divide one by the other, let's say 1 by 2, V naught by I naught, you will get 1 by 2. So dividing 1 by 2, you get the resistance relationship, and that is what we are looking for. So this gives R naught is V naught by I naught. V naught by I naught will be R naught, and Vt by It, Vt by It, and 1 by 1 minus D by 1 minus D will become 1 by 1 minus D square. So Vt by It, Vt by It is nothing but RT as seen from the PV panel side. So I will put it as RT by 1 minus D whole square. So this is the crucial relationship that we would like to use for maximum power point tracking. Now let us look at this this whole circuit from the viewpoint of this resistance relationship. Let us now see what is the effect of the boost converter on the MPPT through the IV characteristic curve. So I am replacing the boost converter by a block, and we have the load resistance R naught like this. So this is R naught, you have the voltage across the output V naught and the current through R naught as I naught. The impedance seen from the input side is RT here, and the boost converter is having a control input D. And we have just now seen that RT, the terminal resistance on the input side of the boost converter, is equal to R naught into 1 minus D whole square. So now let us draw the IV characteristic. Vt, the terminal voltage on the x-axis, this is terminal voltage Vt, and the current through the terminal, current through the PV panel and the terminal on the y-axis, that is It. So let me draw a sample IV curve and a PV curve. This is the IV curve and the power curve with a peak power point here. I am also drawing the load line 1 by RT that the panel has to see for peak power point operation. So the point of intersection is the operating point, and a line dropping down to the power curve will give you the peak power point, and is the peak power operating point. Now let me draw another load line here. What happens to RT when D is varied? So if D is 1, then you know that 1 minus 1, RT becomes 0. So when RT becomes 0, the slope becomes infinite, so it is aligned along the y-axis, which is going to result in an operating point which is here, which is the short circuit operating point. So it is behaving when D is made 0, whatever may be the value of R0, the load line presented to the PV panel is a vertical line which is resembling a short circuit, virtually a short circuit. So let me indicate that. So this is RT. Now this occurs at D is equal to 1. Now what happens when D is equal to 0? So when D is equal to 0, you see that RT is equal to R0. RT is same as R0. So this happens at D is equal to 0. So from this extreme load line to this another extreme load line, the load line can be varied by varying D. At different values of D, the load line, different values of load line occurs with different slopes, and they intersect at different operating points, and you have different operating points coming in here. And if I drop down a vertical from the limiting load line down here, you will see that these are all the power points that are accessible. So with a boost converter, in the boost converter operation, these are the accessible power points, and these are the operating points that are reachable by the boost converter. So any of these operating points can be reached. However, these operating points here, which I am showing right now with the mouse cursor, they are not reachable by the boost converter. So it is very essential that the extreme 1 by R0 load line falls in such a way that a vertical drop down to the power point is on the other side, that is, it is on the other side of the peak. It should be noted that the peak is in the reachable portion of the operating point. Then the boost converter has meaning and you can use it. So to all this portion, this is called the range of the boost converter. Now there can be a problem. You have to be cautious and check about that. So I have here the IV characteristic with a limiting load line 1 by R0 line here like this. So if I put 1 by R0 line like this, then this is at duty cycle D is equal to 0. So the boost converter, all the reachable points should be on the left side of that, as we saw by the argument just now. So if I draw a vertical from that point, you will see that all these are the reachable operating points. You can have the load lines of different slopes going on towards infinite slope, and the power points that can be reached are these power points. Obviously the peak power point is not within the is not within the zone of operation of the boost converter, so it will result in an operating point which is not reachable. Therefore, in this case, the boost converter, if it is used, will never give you a peak power point, will never give you will never be able to utilize to the fullest extent the PV module or the PV panel. as the converter cannot give a load line, an equivalent load line, which will match the peak power point. Therefore, you should be careful and check whether the boost converter can be used for a given application or not by the load line analysis first, checking the limits of the load line before actually deciding on the type of the converter.